So you'll do a problem in WebAssign eventually that will ask you to compute the torque for something, and in particular, the magnitude of the torque. Remember, the torque itself is actually a vector, right? Where you have like the vector R, which is representing the kind of shaft of whatever it is you're cranking on, correct? And it's as long as it is from the point of rotation to the place where the force is applied. And then you have the force vector itself, and the amount of torque is the magnitude of the torque vector. The torque vector is R crossed with F, okay? And I will say, well, I don't know, let me just go back. I'll show you this real quick just because I'm already talking about it right now. So like this picture that I had at the end of section 4 of chapter 11, this one right here. Let me just kind of point something out here. So what we said was, look, basically, you almost want to think of this force vector as being moved back here. Okay, so here's F reimagined. And of course, you know, if I were to draw R in here again, I would have this. And of course, the area of this is in some sense indicative of the amount of force that's being applied at this point of rotation right here, okay? And what's interesting, if you compute, so let me just, I don't know, let me use red just so it will stand out. So tau is the torque vector. That's going to be R crossed with F. And we talked about, look, if I think about R crossed with F, which way does that point? Okay, I put my arm in the direction of R. I rotate my arm so that my fingers can curl towards F, okay? And I get something that points how? Well, I'll use black here. It's going to point out, yeah? Okay, so this thing is perpendicular to this and to this, and it points out. So this is tau, okay? And what's interesting is most bolt systems actually, I mean, think about it. If I'm applying, look at that foot pushing down right there. You guys know lefty loosey, correct? Yeah? Which way is the bolt going to be turning if I push down on that thing? It's going to be turning to the left, and it's actually going to be coming out. Does that make sense? So the way that we orient the torque vector usually is in line with kind of the righty-tighty, lefty-loosey thing. My grandpa taught me that. Have you guys ever heard that before? If I turn sort of a rotating bolt to the right, it will go in. And if I turn it to the left, it will go out. And it turns out the torque vector typically will obey that rule. Unless sometimes you'll have a bolt that's kind of inverted upside down and it will actually operate in the opposite way, okay? But you can see that the torque vector is actually pointing in the direction that the lug nut will come out at this point, yeah? Just wanted to point that out. So the magnitude of the torque is the magnitude of that cross product. Any questions on that? I'm not even going to do an example. There'll be one in WebAssign that you kind of work through, but you at least have the formula. But any questions on that? So torque itself is technically a vector. Now, the torque my grandpa talked about when we would work on cars was really not a vector. He was, I believe, unless he was like, right, I mean, he was not talking about vectors. When he would talk about torque, it was always a number, yes? And so what he really meant was the magnitude of the torque, yeah? All right. Just wanted to kind of point that out real quick. And now we are going to go into some more applications in the realm of lines and planes, okay? So we're in section 5 of chapter 11 at this point. And by the way, we have this section and 2 others, and we'll be done with chapter 11, and we'll just be ready to take that 3rd test that I kind of warned you about, right? It will be over chapters 10 and 11. And remember, I never asked you about the very end of chapter 9 either. I will be at liberty to ask you something about power series which was at the end of chapter 9 before. That will appear on the third exam, okay? So power series, chapter 10, which was on like parametrized curves and whatnot. And then chapter 11 was on all things vectors. That will be the content of the third exam. And the reason I organize things in this way is so that you will just be able to nail that final exam. You won't have to study as much stuff, and you'll just be ready to go. You'll just have to go back and study integrals from chapter 8 and the first stuff about series from chapter 9 and a little bit from chapter 12. But the third exam basically jumpstarts your studying, okay? Any questions on that before we move on here? We still have 3 sections, but yeah. It will probably be like next Friday or something like that. I think, is it on the schedule? The next Thursday? Which Thursday? Oh, okay. Well, probably Friday or something like that. But I think that's when things will work out. Yeah. Yeah. I mean, it might work out that it would be the 5th, but I think Friday is probably going to be a better bet. Hey, let's talk about lines and planes. Okay. So for equations of a line in space, we'll look at a couple of different options. One will be something called the parametric equation of a line. And then there's going to be the so-called linear equation for parametric equations of a line, and we'll actually go back and forth between that and a couple of other options. There's going to be the parametric equations. There's going to be something that we call the vector equation. And then there's going to be something else we'll call the symmetric equation. You'll have lots of options for equations of a line in space. When you're in 2-dimensional space, you had a couple of options as well. Do you remember? You had like the slope-intercept form, but you also had the point-slope form. And what we'll realize is that those 2 options are really in line with what we're going to talk about here in 3-dimensional space. Then we'll talk about linear equation for a plane in space as well, okay? We'll talk about sketching planes. And finally, we'll finish with distances between points and planes and lines in space, and actually compute the distance between these various objects in space. It'll be a good time for sure. We'll have all the power that we need in the form of vector stuff, like dot products and cross products will be just the thing we need. All right. So if we were in the XY plane, what kind of information did you need to write down the equation of a line? What did you need to write down the equation of a line? Okay, slope and y-intercept, okay? So that would have done the job, yes? Slope and a point, okay, I'll say or, right? Slope and y-intercept would have done the job for sure, yeah? Or slope and point, okay? Yeah, Michael. Or just 2 points. Or, right, or 2 points. Yeah, or 2 points. That would have done the job. Okay, so that was in the XY plane, yeah? Now, here's the thing. Slope is sort of an ambiguous thing in 3-dimensional space. This makes sense in 2D, okay? Slope is something that makes sense in 2-dimensional space, but in 3-dimensional space, what do you mean by slope? Because if I'm at a point and I say go up at a slope of 2, you would say, what? Which direction and do I go? Do you know what I mean? It's like, do I go that way or that way? I mean, I have too many options, yeah? If in 2-dimensional space, if I'm at a point and you say go up at a slope of 2, you would know that that means move in a left to right fashion, and for every unit of movement in the positive x direction, go up 2 units in the y direction. You would have a very clear idea of what was going on there. So slope is not so clear in 3-dimensional space, okay? But slope in 2-dimensional space really was a vector. Even though it was one number, it was really a vector. You just always knew what the x coordinate was. So like, what was the notation we used for the slope in 2-dimensional space? What was the letter? M, okay? And I'm telling you, this just means that for each unit of movement in the positive x direction, we move how far in the y direction? Move how far in the y direction? So like each unit of movement in the positive x direction should result in how much movement in the y direction? M, whether M is positive or negative, right? You move M units in the y direction. That's what slope means, okay? And so we can capture this in a vector, okay? And what vector is it going to be? Well, so capture, that's the word capture right there. You go, okay, if I move 1 unit in the positive x direction, how many units do I move in the y direction? Notice I'm not saying positive y. I'm saying just units in the y direction. In the y coordinates, directed distance, yeah? So for every 1 unit you move in the x direction, how many units do I move in the y direction? M, okay? And this guy right here, even though we've never talked about this before, this is called a direction vector for the line. It kind of tells you the direction the line is moving. If this was 1, 2, you would know that this was a line of slope 2, yeah? If it was 1, 2, you would know this was a line of slope 2, for instance, okay? If it was 1, -3, you would know that this was a line of slope -3, okay? So this slope business can be made more precise by thinking of it as a vector. We really could have done that all along, but we didn't really need to until now. Now that we are like in 3-dimensional space, we don't have as clear of a direction of what slope means. But slope really all along has meant a vector that has x as its x coordinate as 1 and its y coordinate as that slope number. Yeah? Does that kind of make sense? So what do you think we're going to have as slope, in quotation marks, for a line in 3-dimensional space? It's not going to be a 2-dimensional vector. It's going to be a 3-dimensional vector, yeah? It's going to be a 3-dimensional vector that's going to tell us the direction of the line, okay? We're going to have a vector that's literally going to be telling us the direction of the line itself. Okay? And that's going to be called our direction vector, okay? And by the way, slope, okay, if I take this new idea of slope captured in like a direction vector, all of these things would still be sufficient to describe a line. Do you know what I'm saying? Except maybe the y-intercept one. I mean, what in the world would that mean, right? But definitely a slope and a point and 2 points would be enough to determine a line in 3-dimensional space. So this means I can have a point and a direction vector, i.e. the slope, or I can have 2 points. But of course, the 2-point situation, I really could just take the 2 points and figure out what the direction vector is for the line. Does that make sense? I could kind of create a vector with those 2 lines, and that would be my direction vector. And then I could use either one of the 2 points to really be in the situation where I have a point and a slope, i.e. a direction vector, okay? Does that make sense? We're gonna look at lots of examples and we're gonna develop this in full detail, but I just wanna give you an idea of what's happening. So like, I mean, here's kind of a picture of what I'm thinking. So you had a line before in two-dimensional space, okay? Really you had a vector on this thing. There was a vector that kind of described, that described the slope of this line. So this vector right here is the vector 1, comma, m, okay, where m is the actual slope of that line. Yeah? Okay? All right. Moving on. Slope and a point or 2 points, okay, which is what we already said here, but, now we're going to see what happens in three-dimensional space. In space, we also need the slope, i.e. direction, and a point, or 2 points would do the job. Okay, so we have any point, and we have a vector that is in the same direction as the line. And what did I say we call this thing? What do we call this guy right here? It's called the direction vector. Okay, sometimes people call it the slope vector, okay? And oftentimes we notate this thing by V for the direction vector, okay? So we have ABC as our direction vector, and we have a point on the line x1, y1, z1. If somebody handed us 2 points, we could still figure out the direction vector from that by computing the vector between those 2 points, okay? All right. Any questions on that? We're going to start using this and develop an equation of a line in space, but any questions before we move on? Okay, so look, here's kind of the general, it's called the parametric equations of a line. You might say to yourself, where does that come from? So x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct. And by the way, t is any number. So t is any real number. Okay? This is going to sketch out a line in three-dimensional space. Okay? How is this working? Well, it's like this. Okay, so suppose this is my line, like this. Okay? And suppose this is my point, x1, y1, z1, and then I have my vector, my direction vector. Let's see. This is v, which is equal to a, b, c, like this. Okay? Well, look. Let me draw the rest of the coordinate system here just so I can illustrate. Okay, so there's y and there's x right there. Okay, so this is z, x, y, like this. Okay, and here's the thing. How do I describe any point on this line that we've drawn? How do I describe any point that happens to be on this line? Well, watch, I'll show you. What I can do is I can draw a vector kind of coming out to this point. Okay, what are the coordinates of that vector that I just drew? What are the coordinates of that vector that I just drew? Since they end at the point x1, y1, z1, and they emanate from the origin, it emanates from the origin, what are the coordinates of that vector? What are the coordinates of that vector? That green vector that I just drew, what are the coordinates of that vector? Angle bracket x1, y1, z1. Yeah? Okay, so angle bracket x1, y1, z1. Okay? And then I say, okay, I want to know how to get to any other point. I want to know how to get to any other point on this line. Okay, like that point that I just drew, that black point right there. How do I get to any other point on that line? Well, what I could do, okay, what I could do is I could just say, look, you know, if I go from x1, y1, z1 out to this point, you know, that vector that I just drew, that kind of black vector that's an extension of the blue v vector, that's going to be some multiple of the blue vector. Do you see that? Okay, so for instance, there's some kind of t for which that black vector right there is t times v. Okay? And then what you say is, look, you know, let me just draw this vector right here. Okay, so that vector that goes out to there, and I'm trying to draw this thing so that it kind of makes sense. That vector that I just drew right here that goes out to that point, it's really, if you think about it, it's x1, y1, z1. It's that vector plus t times that vector. Yeah? I mean, think about it. It's the third side of that triangle right there. I have x1, y1, z1 as a vector, and I've added the vector tv to that to get to this point that happens to be on that line. Okay? But what is that? That's just, you know, x1, y1, z1 plus, okay, t times that vector. That's just ta, tb, tc. Okay? And then if I add those things together, I'm going to get x1 plus ta, or at, comma, y1 plus bt, comma, z1 plus ct. And now you see where these things come from. What is the x-coordinate of any point on that line? Well, it's going to be x1 plus some multiple of a. What is the y-coordinate on that line? Well, it's going to be y1 plus that same multiple of b. What is any z-coordinate of something on that line? Well, it's going to be z1 plus that same multiple of c, where a, b, and c are the coordinates of that direction vector. Okay? You see that little triangle right there? You have the green vector, you have a multiple of the blue vector, and I can get to any point on that line by simply adding those two vectors together. Yeah? And I kind of figure out what the x-coordinate, y-coordinate, and z-coordinate are of that vector. Okay? This thing right here, so x1, comma, y1, comma, z1 plus t ABC, right? This is oftentimes referred to as the vector equation of the line. Okay, and the parametric equations come from that just by combining the x, y, and z coordinates of this thing. Okay, all right. Okay, any questions on that? I mean, look, it's just, you have that triangle picture right there that's describing the whole situation. But any questions on that? We're going to do some examples here, but I just want to make sure that this is somewhat clear. Okay, so answer this question. Identify 2 points on the line using t equal to 0 and t equal to 1. Okay? Identify 2 points using t equal to 0. So if I plug in t equal to 0, what do I get? What if I plug in t equal to 0, what point do I get? Yeah, x1, y1, z1, yeah? And what if I plug in t equal to 1? Yeah, x1 plus a, y1 plus b, z1 plus c. Those 2 points are going to be on the line. What are those points? Well, let me just kind of redraw the picture again, okay? So here's X, Y, and Z. I'm going to draw my line in three-dimensional space like this, okay? I'm going to single out the point X1, Y1, Z1, and X1 plus A, Y1 plus B. Okay, so X1 plus A, Y1 plus B, Z1 plus C. What is that? What is the segment that joins those 2 points? Think about it. How many units have we moved in the X direction in moving from the one point to the other? A units. How many units have we moved in the Y direction in going from one point to the other? B. And we've moved C units in the Z direction. So the points, the segment joining these points, that right there literally is the direction vector. And that's V equal to ABC. Okay, so that's like the direction vector right there. I just want to make sure that it's clear what's happening here. Okay. So, I want to go down to two-dimensional space and revisit this. Oh, by the way, let me just say, so think about this for a minute. If I take the parametric equations and I solve for t, so think about this for a minute. If I solve the first one for t, I'm going to have x minus a over x, or sorry, that's not what I meant to write. X minus x1 over a is equal to t, yes? But what else is equal to t? Remember, t is the parameter, yeah? So t is like the scalar multiple we took of the direction vector. If I solve for t, I get x minus x1 over a has to be t, but also y minus y1 over b is equal to t, and z minus z1 over c is equal to t. So all three of those things have to be equal to each other, okay? In order to write down these things, I would have to have a, b, and c be non-zero, okay? But of course, if c was 0, think about it for a second. If like c was 0, then what would z have to be equal to all the time? Like if c was 0, then what would z have to be equal to all the time? Z1. Z would always have to be equal to that number Z1, okay? So you could kind of just list that as a separate part of the line itself, okay? So to write these so-called symmetric equations down, you would need for A, B, and C to be non-zero so that you could actually divide by them. But the whole point is all of these are actually equal to T, the parameter itself. So you can easily flip back and forth between the parametric equations and the symmetric equations of the line. All right. All right. So I have a little link to GeoGebra in here because you can sketch lines in three-dimensional space in GeoGebra. Okay, and I would sort of encourage you to go over there. We'll do some examples ourselves, but I want to look at an example in two-dimensional space. Okay. So look, what if I said, so what about the line y equal to 2x plus 1, okay? So what would be the direction vector for this? Think about it. The slope is 2. What would be the direction vector for this thing? I'll give you a hint. The x-coordinate is 1. What's the y? So for every 1 unit of positive x movement, how many units am I going to have in the y direction? 2. Okay, so this is the direction vector for this thing, okay? And what is a point on this line that, you know, is kind of an easy point? So what's a point on this line? Point. For instance, if I plug in x equal to 0, 1, right? So that's the so-called y-intercept of this thing, yes? So if I were to graph this line, okay, so first of all, it goes through 1, let's see here, y equal to 2x. So, I mean, if I'm at -1, that x is -1, I'm down here, okay? So this is what the graph of this line looks like. Okay. Now the thing is, so here's my point 0, 1. And actually, if I wanted to draw the direction vector, which is, 1, 2, hang on, let me erase this little arrowhead on here and make this a little bit longer. Okay, if I wanted to draw the direction vector on this, I would say, okay, for every 1 unit of movement, I have 2 units of movement in the y direction. Okay, so there you can see a point and a direction vector, yes? If you wanted to have the vector equation of this line, the vector equation of this line, you would think of the point 0, 1 as a vector emanating from the origin. Okay? You can think of the point 0, 1 as a vector emanating from the origin, actually, kind of like what I'm drawing right now. Okay? And then every point on this line could be gotten at by kind of taking multiples of the direction vector and looking at the third leg of that triangle and thinking about that point that forms the terminal end of that vector. So this would be like 0, 1, right? 0, 1 plus any multiple of the direction vector, which is 1, 2. And if I put these things together, I would get 0 plus t. Okay, and then in the y coordinate I would have 1 plus 2t. Okay, so look how stupid this is. The reason we don't do this in two-dimensional space is it all collapses. This would be my x, this would be my y. So the parametric equations in this case would be x equal to 0 plus t and y equal to what? What would y be equal to? 1 plus 2t. But then you say to yourself, that's ridiculous. X is equal to t, so I might as well not even have this other variable t. Do you see what I'm saying? Like I would just plug in t equal to x and I would get y equal to 1 plus 2x. Do you see what I mean? What would the whole so-called symmetric equations look like? Well, the symmetric equations are gotten at by solving for t. Yeah? Okay. So what do you have? You have t equals x, but what else is t equal to? If I solve the y equation for t, what would I get? What would I get? Right? I mean, look, this guy right here is trivial to solve for t. But what if I solve the y equation for t? What do I get? Y minus 1 over 2. Those are the symmetric equations. But do you see this is ridiculous? I mean, if I multiply through by 2 and then add 1, what do I get again? Y equals to 1 plus 2x, or 2x plus 1, yes? So here it's like, technically we had the vector equation, the parametric equation, and the symmetric equation, even in the two-dimensional case. But, it was silly to do that because everything just became a relationship between y and x before. But in three-dimensional space, it's a lot more complicated than that, okay? All right? Okay, any questions on that? All right, let's do another example here, and I'll do another one in three-dimensional space. Okay, so here's another example, or another one in two-dimensional space. What if I had y equal to negative 4, or I don't want to do negative 4. That's too crazy. Okay, so y equal to negative x plus 3. Okay, well, the picture here is like this. Okay, here's 3. Okay, and the slope is -1, correct? Yeah? So if I plug in 1, then I'm at 2, yeah? Okay, so actually, here's the graph of this line. Okay, so what is a point on this line? What's an obvious point? Yeah, 0, 3. Or let's do something else just so that it's not boring, all right? Let's do another one. I don't know. I put another point on there like 1, comma. If I plug in x equal to 1, what's the y coordinate? 2. Okay, and what is the slope? Right, the slope is -1. So what is the direction vector? Well, for every 1 unit of movement in the x direction, how many units do we have in the y direction? -1. You see? Yeah? Okay, and I could actually draw this direction vector on here. Like if I move 1 unit, if I move 1 unit in the positive x direction, I'm going to get 1 unit down in the y direction. So that is the direction vector to this thing. Okay. So what's the vector equation? Well, the vector equation, again, that's kind of thought of as kind of taking this point 1, 2. Okay, I can use any point and then taking any multiple of this vector v. Okay, any multiple of this vector v. I don't know. So that, that's like TV, for instance. And then, of course, the result, well, let me use a color that's going to stand out. Well, I'll use yellow, okay? The result is the sum of those two vectors. Okay, so that vector right there, let me label it. That thing right there is going to be the vector 1, 2, okay, which is the green thing. In fact, let me write that in green just so it makes sense. Okay, it's going to be the vector 1, 2 plus in blue t times the direction vector, which is 1, -1. And if I add those two things together, I get 1 plus t, comma, 2 minus t. Do you see that? Yeah? Okay. 2 minus t, if I kind of combine those things. What I basically did is I distributed t and combined x and y coordinates. So in other words, the vector equation ends up being 1, 2 plus t times 1, -1. Okay. What are the parametric equations? Well, that's gotten at by taking x equal to this first thing and y equal to the second thing, yeah? So what am I going to get for the parametric equations? Well, it's going to be x equal to 1 plus t and y equal to 2 minus t, okay? And then how do I get the symmetric equations? What do I do to go from parametric to symmetric? What do I solve for? T. Okay, I solve for t. Okay, and so that would give me x minus 1 in the first case, yes? That's easy. And what would I get if I solve for t in the second case? Y minus 2 over, would be y minus 2 divided by -1. You see what I'm saying? Yeah? And of course, I mean, you guys realize that this could be simplified a lot, right? So this is the same thing as if I multiply through by -1, 1 minus x equaling y minus 2, which of course is the same thing as y equal to 3 minus x, which is exactly what we started with. Okay, y equal to 3 minus x, which is exactly what we started with. Yeah? So the vector, parametric, and symmetric equations all existed before in two-dimensional space, but we just weren't making that explicit. You see what I mean? Hopefully. Okay, well, that just was not being made explicit before. All points on this line can be reached by taking that green vector, which is basically a point on that line emanating from the origin, and adding any multiple of the direction vector. And that gives us everything we want to know about this line. Okay? Basically, the only thing that we worked with before was essentially equivalent to the symmetric equations of a line. Yeah? All right? Any questions on that? Questions? I think I'm going to stop right there because tomorrow we'll talk a little bit about planes. We'll do a couple of examples of lines in three-dimensional space, but it's really not going to be all that different from what we did right here. And we'll also sketch some things in three-dimensional space.